I hope you had a nice lunch. Just to remind you that before the lunch, we were finishing all the concepts related to the audit of operations. I see that by the end of the morning, there was still one question in the chat. Is the projected error or the maximum error that matters for materiality? Well, if I understand the question, both, I mean, to decide if the population contains or not material error, you have to use both the projected error and the upper error limit, and you already know that is this combination that may guide you in your decision. If they are both above materiality, we conclude that there is material error. If they are both below materiality, you conclude that there is no material error. If one is below and another one is above, there is not sufficient base to conclude, results are inconclusive, and some kind of, maybe need some kind of additional analysis may be needed. By the way, I have just shared with all of you the copy of this presentation in the chat tool, okay? So you should see it in the chat tool and you can download it. Now, let's start talking a little bit about sampling techniques. We still have lots of topics that will be very difficult to cover during the day, but let's try to cover as much as possible. Some of the topics I have to resume a little bit so we can advance to more technical stuff. First of all, to tell you that the sampling methods that are available for the audit authorities and are in our guidance note are in the branch of statistical sampling, and two sub-branches, equal probability selection and probability proportional to size. And inside these two branches, we have, under equal probability selection, we have simple random sampling and difference estimation. And under probability proportional to size, you have one proeminent method, very well known, which is Monteiro unit sampling. In any case, I have to tell you that during the last years, difference estimation has decayed and it's no longer used by almost any audit authority, and for the new programming period, we have even not included it in the delegated act, and we have just proposed simple random sampling and Monteiro unit sampling, being very clear that the audit authorities are absolutely entitled to use, if they want, difference estimation, but also other sampling methods that are not covered in these documents. But if they are acceptable sampling methods, they are, of course, accepted by the Commission. In the branch of non-statistical methods, we have random and non-random selection. You already know that non-random or non-probabilistic selection is forbidden for the substantive testing, which means that we have to select, even in non-statistical sampling, we have to select units with probabilities. And in this framework, we try to mimic what you do under the statistical sampling. I mean, under non-statistical sampling, we either use equal probability selection, like in simple random sampling, or probability proportional to size selection, like in MUS. So in a way, doing non-statistical sampling is nothing more than doing a simplified version of simple random sampling or MUS with two particularities. One is that we don't use a formula to properly calculate sample size. And the other one is that the precision is not calculated, and therefore we cannot calculate the upper error limit. I think someone had difficulty to download the presentation. You just need to click on it and it will be, and you can automatically open it in principle. So finally, under these dashed lines, you have two things: stratification and multivariate approaches. Again, we don't have time in this basic training to cover all of this, but stratification, it was already explained in the morning, is a technique where you divide the population into subpopulations with the goal of reducing sample size, improving precision, and assuring that all the strata are represented in the sample. And multivariate approach is unfortunately something that we cannot deal in this seminar, but let's say it's very much the standard now used by most of the audit authorities, which are versions of these basic methods where the audit work is not done in one single period, but it's spread over the year into 2, 3, or more sub-periods during the year, with the big advantage of avoiding all the audit work to be concentrated by the end of the year. And these techniques, both certification and multi-period approaches, can be used in combination with any of the sampling methods. So you can have certified versions of simple random sampling or MUS, multi-period versions of both methods, and so on, or even the combination between certification and multi-period approaches. Next couple of slides is a little bit a summary of what you can find in the guidance note on sampling. I will skip that and remind you that for the remaining of the afternoon, we are going to have a focus on statistical sampling, but also talk a little bit about non-statistical sampling. But within statistical sampling, we will focus on simple random sampling and multi-unit sampling. Whatever is the sampling methods, the only difference between sampling methods are technical details. But the general strategy of any sampling method is always the same. So I could say, maybe simplifying a little bit, that we have 6 major steps, and that these 6 major steps that I have spread over these 2 slides are basically common to any sampling method. So in any case, we always start to define the objective of our substantive test, which is basically to estimate the amount of error in declared expenditure and to conclude if the population contains or not material error. We have to define the population, which corresponds typically to a program or a group of programs in a certain accounting year. We have to define the sampling unit. Very often the main sampling unit is the operation, but can be the project, the payment claim, and the subsampling unit, if used, can have different forms. To set up the system, we have to define some population parameters. For instance, the tolerable error that we have already talked about, which is 2% of the expenditure. The anticipated error that we have already talked long about, it should be as realistic as possible. The confidence level that we already know that is related with our assessment about reliability of the control systems. And to set up the system, we also need a measure of the population variability. So an approximation about the standard deviation of the errors or the error rates, whose approximation is based on the same sources as the anticipated error. I mean, it's based either on historical data, pilot samples, or professional judgment. Then with all of these, we calculate a certain sample size. Then we select the sample and we perform the audit. And then we project the results to the population. We calculate precision and we draw our conclusions. The only difference between methods are some technical details, because the strategy itself, the steps themselves are exactly the same for all the sampling methods. And it was said before, the sample size is mostly dependent on 3 things that now you already know very well. Confidence level, the higher the confidence level, the larger the sample size. The variability of the errors in the population, I mean, the larger the variability or the more heterogeneous the population is, the larger the sample size. And the planned precision, we already know that the smaller the planned precision, the larger the sample size, or using other words, the closer the anticipated error is to the materiality threshold, the larger the sample size, as we have very well spotted in that graph that was of a symmetrical nature and was always growing the sample size towards the materiality threshold of 2%. So let me now go a little bit further into the details of the methods. In our guidance note, we have 2 variations for multi-unit sampling. The most traditional way to perform multi-unit sampling is what in our guidance note we call conservative MUS now. I would say that almost no audit authority is using that method presently, or maybe I can even say no audit authority is using that method, I'm not sure. Why? Because several years ago, when we have introduced this new variation that we decided to call the standard MUS, we have seen that this method had several advantages in relation to the traditional conservative MUS version, and I will tell you some of the variations. This is so true that for the post 2020 we only have covered the standard MUS in the delegated act. But anyway, there are two versions of MUS. And what are in the following minutes I would like to discuss with you the favorable conditions that justify the use of MUS or justify the use of simple random sampling or the other methodologies, which is basically a very important question. When should we use a method with probability proportional to expenditure like MUS, or when should we use simple random sampling? Well, MUS tends to be a good method when two conditions hold at the same time. First condition, the values of expenditure, sorry, I'm going to start with the second one. The values of expenditure per operation vary significantly, have high variability, which is logic. I mean, if the operations have more or less similar expenditure, there is no point in selecting MUS. MUS is a method that is going to select more frequently the larger operations and less frequently the smaller operations. Now, if this is true, this means that we can only profit from this characteristic of MUS in situations where the operations are very different from one another in terms of expenditure. This condition is important to make sense to apply MUS, but it's not enough. There is a second important condition, which is the MUS method only works well when the errors tend to be approximately proportional to expenditure. In other words, if you want to say, when there is a positive correlation or association between errors and expenditure. So in situations where we expect that larger operations on average tend to show larger amounts of errors and that smaller operations on average tend to show smaller amount of error, MUS is a good method. And to be honest, for the ones that have some experience now, it is very frequently the case. I would say that in majority of the populations of expenditure that we have seen in our lives, it is true that on average, larger operations tend to show larger errors, small operations tend to show lower errors, and this is why MUS is such a popular method in the world of audit. It's popular because it's efficient. And it's efficient because usually these two conditions together hold. On top of these two conditions, the older version of MUS, the conservative MUS, also had additional conditions. For instance, conservative MUS can only be applied if the error rate is expected to be significantly below 2%, can only be applied in situations where the proportion of operations with errors is expected to be very low. So let's say conservative MUS have additional conditions. These are, among others, are some of the reasons that made this method less popular these days, but probably the most important reason why this method is less popular is because it tends to produce larger sample sizes than the standard MUS. When shall we apply a method based on equal probabilities or a method like simple random sampling? Well, we apply simple random sampling as an alternative to MUS whenever either you don't see big variability in terms of the expenditure of the operations, or if you see this variability, you don't see or you don't expect to see a strong positive correlation between errors and expenditure. But sometimes the correlation is very low, or even sometimes the association is negative. I mean, many of you may have seen in your professional life situations where the larger operations tend to show smaller amount of errors, and smaller operations in terms of expenditure tend to show larger amount of errors. This happens. It's not probably the most frequent pattern, but it happens. And when this happens, MUS is a very bad method. And in this case, simple random sampling is much more efficient, with the advantage that simple random sampling can be applied with two, let's say, sub-options in terms of projection of errors, either mean per unit estimation or ratio estimation.
Finally, non-statistical methods are applied for smaller populations, and stratification, as I stated before, is applied in combination with any of the above methods in order to reduce sample size or improve precision whenever you expect that different groups in the population will tend to show different levels of error amount or error rate. And finally, unfortunately, not to be covered in this seminar, but very importantly, this is today our most standard method to use in any of the audit authorities. Multivariate sampling can be also, like certification, can also be used in combination with any of these methods in order to guarantee that we are able to spread audit work over the year and avoiding the concentration of the audit work by the end of the year. It's very important to make this clear that multivariate approaches usually do not contribute to reduce sample size. The goal of reducing sample size is attributed to stratification. Multivariate approaches do not reduce sample size or can even slightly increase sample size. The advantage of multivariate approach is to allow us to spread the work over the year instead of concentrating by the end of the year. But there is also something that several of you have done, several audit authorities, which is using a combination between stratification and multivariate approaches. And by doing this, we can achieve both goals. Through stratification, we can improve precision or reduce sample size. And through multivariate approaches, we can spread the work over the year. Some notes, additional notes. Some additional notes for you. It's important to state there is not a universally best method. There is not such a thing as a method that is superior to the others. We cannot state that MUS is better than simple random sampling. Depends on the population characteristics. That's why it's good. It's a good deal to always think a little bit about our populations, about our historical data before taking a decision about what is the method that we want to use. A good thing to know is that there is not also such a thing as a wrong method. To be honest, whatever is what are the population characteristics, you can always apply any sampling method and they will all work. Well, of course that you can tell me, but if they all work, why do we care about choosing a method? Well, because although all the sampling methods work, if you not choose the best sampling methods, there is a price to pay to do the work with a method that is not so much suited for your population. And the price to pay in our trade is paid in sample size, in audit work. I mean, you can always do the work, but to do this work, you have to work with a sample size larger than the one that would be necessary if you choose a better method. That's why it's always a good thing to think a little bit about your population. I'm going to skip these details because we have already discussed when to use stratification, whenever we believe that there are some subpopulations, some groups in our populations that have more errors than the others, and whenever we can spot these and we divide this population into subgroups, it's always a good deal, and it will always offer us better precision in smaller sample sizes. In terms of non-statistical sampling, I will address this in more detail later on today, but you already know this is reserved for small populations. The threshold depends, will change for the next programming period. Tomorrow we are going to talk about that, but for the 1420 that is finishing, the threshold for non-statistical sampling has been arranged between 50 and 150 operations, meaning that for populations smaller than 50, we typically use non-statistical. For populations above 150, we typically use non-statistical. And in the between, we take a case-by-case decision, take into consideration the effort, the reasonable effort that if the effort to perform statistical sampling is reasonable or not in comparison with the importance of that small population. Anyway, there are different things that you can do to increase the population size in order to achieve sufficient size, changing the sampling unit from operation, for instance, to payment claim, or grouping different programs in one group, and by doing this, increasing the population size. And more importantly, if in the beginning of a programming period, you don't have enough population size to apply statistical sampling, you can start with non-statistical, but once you get size enough, you should automatically change from the non-statistical approach into the statistical approach. Let me address the question, is it possible to use stratification instead of multivariate approach? Well, I understand your question. To be honest, a multivariate approach is nothing more than a particular case of a stratification. So all the methodology that we have proposed to you in our guidance note on sampling, all the templates that we have prepared, they address multivariate approaches like a particular case of stratification. So in practice, it's stratification, but it's a very special stratification that has many different particularities because it's a stratification where some stratum are only going to happen in the future. And there is a lot of uncertainty in population parameters that are still unknown when you plan the sample size. This is not something that happens in traditional stratification where the population characteristics are already known or can be directly accessed from pilot samples in multivariate approaches. Although to some extent we can consider it stratification, it has particularities that lead us to design it in a specific way that, of course, in detail we cannot discuss in this seminar. And that's it. Based on this, we have then an overview of the available existing sampling methods, and now we will be in conditions. Let's see if you have for how much you have time today to present to you an overview of the, let's say, 3 or 4 most important and basic sampling methodologies. One for simple random sampling, one for MUS, one for stratification, in our example, combining stratification with MUS, and finally, the general approach for non-statistical sampling, okay? There are 4 topics, let's say, more technical topics to cover. These topics will be addressed sequentially. Let me see another question. I thought the threshold for 1420 was 150. No, it's not. It's a range, okay? And we, of course, then I don't know the practice of all audit authorities, but you have, the audit authorities are encouraged to, in the between 50 and 150, to think a little bit about the pros and cons about using statistical and non-statistical methodology. Of course, that in between 50 and 150 is very customary that you choose to use non-statistical sampling, but this does not need to be the case. For instance, if you have a population of 140 and under statistical sampling, you conclude that you can do the audit with 30 or 35 units, probably it should be a good choice to use statistical sampling, okay? Of course, that if you have a population of 80 and your sample size would be 70, of course, we can automatically conclude that the effort to do statistical sampling is very disproportionate in comparison to the size and importance of this population. So we have this open door, but because I understand, because this threshold in the format of range has always created some doubts for the next programming period. As many of you know, the threshold will no longer be a range, but will be a fixed number, as we are going to discuss tomorrow. So before we start talking about specific sampling methods, and for the rest of the day, please be aware that the presentation will be more technical because I will explain the technical details of these 4 families of methods. Okay. So before I move on, please, any questions? For non-statistical sampling, the coverage I will tell you in 1 hour time or so. I will tell you what are the coverage that are foreseen, that you should consider for the ending programming period, and then tomorrow I will talk about the following programming period. Any comments or additional questions regarding this overview about the sampling method? So now prepare yourselves. Next part is more technical. In more technical detail, what is simple random sampling, how can be applied, and same thing for the other methods. For each method that I'm going to present to you for the rest of the day, we are going to always follow the same strategy. I start reminding you about the method, telling you about sample size calculation, projection of the errors, calculation of precision, evaluation of the results, and I always end with an example, okay? So these steps are always the same for all the methods, and you are going to see all the methods have more or less the same steps in common. What changes from one method to the other is just the technical detail of the formula, how to calculate sample size, on how to calculate the projected error, the precision, and so on, okay? So let's start. Simple random sampling, as you remember, is statistical. It's probably the most well-known among all the statistical methods based on equal probabilities. The goal is to project the errors of the amount of error in the population from the data in the sample. Under simple random sampling, the units are selected randomly with equal probabilities, so you can basically select them. You don't need a software, you can select them directly in Excel or any other way where you have a generator of random numbers. And the idea of this method is that can be adapted to different types of populations. And let's say in the majority of the cases, majority tends to produce sample sizes larger than MUS, but still there is a fair amount of cases where produces sample sizes smaller than MUS. Why? Depends on the relationship between errors and expenditure in the population. If you remember from a few minutes ago, I told you simple random sampling will be more efficient than MUS in situations where the association between errors and expenditure is weak or even negative, and or in situations where the expenditure per operation has low variability. On top of this, I have to tell you that simple random sampling has at least two projection methods that can be used: mean per unit estimation and ratio estimation. And in a few minutes, I will address the advantage of each one and in which conditions we should use one or the other. So, any sampling method, before we select the sample and perform the audit, first step is to calculate sample size. All the sampling methods rely on some formulas to calculate sample size. The formula for simple random sampling, as you are about to see, involves several parameters. Some of these parameters are absolutely well known, while other parameters have to be approximating using auxiliary information. So what do I need to calculate sample size? I need the population size. I mean, how many operations are there in the population, which is always known. I need a parameter from the normal distribution that we call the normal, the Z parameter, sorry, that is associated with the confidence level that we are using. I need a tolerable error. This one is easy, it's 2% of the total declared expenditure. I need the anticipated error that we have discussed a lot during the morning, and it's based on historical data, pilot samples, auxiliary data, professional judgment. And I also need an approximation of the standard deviation of the errors in the population. And the source for this standard deviation is exactly the same as for anticipated error, the same historical data, pilot sample that gives you an insight about what can be the error, also gives you an insight about what can be the standard deviation of the error amount. So this is the formula for sample size calculation. Either you have this in Excel or in any other format, what is important is for you to know what information to feed in. And no doubt about it is the number of operations in the population. Z comes from a table. We will address it in a moment. Tolerable error, no doubt, it's 2% of the expenditure, but among these 5, there are two parameters that are doubtful. The standard deviation of the errors and the anticipated error. Why? Because I don't know their values. If I would know their values, I wouldn't need to do any audit. It would be because I would know the population. So what to do in these cases? Well, I have to approximate both of them, as I said, using the historical data, the pilot samples, the professional judgment, and based on this, I will try to guess as accurately as possible what is the level of error that we expect to find and what is the level of standard deviation that we expect to find. Based on these parameters, I will calculate the sample size. Very importantly, I have not said before, but I will say this now. We very much recommend these days that in case of using a pilot sample, you use a pilot sample of not less than 30 units. Why 30? It's written here from at minimum 20, but we recommend 30. And the reason is very simple. In statistical sampling, the minimum sample size is 30. You cannot use a sample size smaller than 30. So there's nothing to lose in using a pilot sample of 30, because let's face it, if by the end of the pilot sample you conclude that is enough, that's good, the work is done, and you don't need to do any additional work. If by the end of the pilot sample you conclude that your sample size in fact has to be increased, imagine to 40, at least you have already audited 30, which means that you only need to audit 10 more. So there's nothing to lose. Either 30 will do the job and no additional sample is needed, or if additional sample is needed, at least minimizes the size of the additional sample that you have to take. So we always suggest a sample size for the pilot sample of at least 30, or if you already know in advance, based on your past experience, that the sample size will be surely larger than this, you can also increase the sample size towards a value that you consider more close to the final value of the sample size. Now, importantly, for this calculation, these two parameters come from auxiliary information, standard deviation and anticipated error. Tolerable error and population size, there are no doubt about them. What about Z? Well, for Z, as you remember, this confidence level is associated with what you have seen in the beginning of the morning that I call the detection risk and the control risk. So taking into consideration the quality of the control system, we are recommended to use confidence levels in a range between 60 and 90, if you remember. 60 for category 1 systems until 90 for category 4 systems. And we have this table that decodes these confidence levels into values. So automatically I know that if I have a category 1 system and I want to use a confidence level of 60, my Z value to put in that formula will be 0.842, or if I have 71.036 and so on, okay? Nothing else you need to know, just to know that this comes from the normal distribution, but this table allows you to automatically choose a number that you input to that formula. Now, once the sample size is calculated, imagine that you got this sample size of 40. There is still something that some people may forget about and still may allow you to fine-tune a little bit your sample size to further reduce it, which is if your population is small, you can still reduce a little bit your sample size by using this conversion here. Example, as a rule of thumb, I suggest that if your sample size that you have produced from the formula in the previous slide, if this sample size gives you a value that is at least 10% of the population size, imagine that my population size is 400, it's even to make it more strongly, 300 items. So if it is 300 items, 40 is more than 10% of 300. In that case, you can still fine-tune manually your sample size to still reduce it a little bit. It's not a dramatic reduction, but still you can pay a little bit by doing this fine-tuning here. For instance, in my example, 40 times 300 divided by 339. Just for the sake of the example. So for the sake of the example, this gives us around 36. Well, it's not extraordinarily impressive, but it's still good. I saved 4 audits. Instead of auditing 4 operations, you can audit just 36 operations, okay? Of course, that if your population size is 3,000 operations or 30,000 operations, this almost does not have an impact over your sample size, and your sample size will be always 40. But for smaller populations, as in my example, you can still save a little bit of sample size by doing this manual fine-tuning. Okay, so let's assume that we already understand how to calculate sample size. And knowing how to calculate sample size, let's now see how to, and now imagine that we have audited the sample, okay? And we have the sample results, how to project the errors from the sample to the population. And basically you have 2 methods. As I said before, mean per unit and ratio estimation. Mean per unit estimation is based on absolute errors, and the ratio estimation is based on error rates. Someone asked, what is small population? I have already answered. Yes, I have already answered what is the threshold for considering it a small population. Now, projected errors. Either you use mean per unit or ratio estimation. Under mean per unit estimation, we use the absolute errors, and the ratio estimation, we use the error rate. So what does it mean? Well, under mean per unit estimation, you calculate the average error in the sample. So basically, you just sum all the errors in the sample and divide by the sample size, and you multiply by the population size. Under ratio estimation, you calculate the error rate, which is the error found in the sample divided by the audited expenditure. So here E represents the errors and BV the book values, and you multiply the error rate by the book value of the population. So 2 different ways to project the error, either using mean error or average error multiplied by the population size, or the error rate multiplied by the population book value. As you know, in this ending programming period, this is not a free choice. You should choose the method that gives you better precision. And mean per unit estimation tends to be a better method when the errors are very independent from expenditure or even show a negative association. And ratio estimation tends to be a better method when there is still a positive association between errors and expenditure. But how? One thing is to understand the concept. Another thing is to decide, and it's up to you to decide which method has to be used. And there are 2 ways to do it. One is to perform this test. I have seen many Excel sheets coming from your audit authorities, and many audit authorities do this in advance and verify the application of this condition, which is fine. Another option is to calculate everything using both methods, and by the end of the audit, you choose the one with better precision, calculating precision for both methods. An example of ratio estimation. I don't know what you mean by an example. Sorry, guys, from time to time, I tend to see the chat and answer some questions. From time to time, I don't know what you mean by an example. but ratio estimation is basically calculating the error rate in the sample, okay? So dividing the error rate, the error amount by the total audited expenditure and multiplying by the book value. The other one, as I said, is based on the mean value. Now, numerical example, it would be pointless to show you a numerical example. First of all, because I will have an example, and the numerical example does not tell you anything. What could you get from a numerical example? 5 divided by 50 times 500. Okay, it's a numerical example. In this case, the error rate would be 10% multiplied by the book value. It's not relevant. It does not tell you anything. But maybe in the context of a complete example, maybe later on, it may make more sense to you. What is important in this moment is that you understand the concept, which is one thing is an error rate, one thing is the average error amount. This one produces a percentage that you multiply by the population expenditure. This one produces an average error expressed in monetary units that you multiply by the population size. By the end of the day, both project the total error of the population, but one through absolute errors, others through percentages, error rates. But what is important for you is that at this moment, this is not a free choice, and either you use this formula to quantify. Let's not do it now in detail. Just need to know that it's very easy to do this in Excel. You take 1 minute, which is in Excel, you can take the column of the errors and the column of the book values, and you calculate the covariance between them. The covariance is an Excel function that measures the association between them. Then you divide by the variance of the book value, which also given by an Excel function. And then you have this rule, which is if this result is larger than half of the error rate, we have to use ratio estimation. If this result is less than half of the error rate, you have to use mean per unit estimation. I mean, guys, I see that, I don't know, half of the audit authorities use this and the other half use the other method, which is, let's not care about this now. Let's do everything until the end using both methods. And by the end, we choose the method that offers us the best precision. It's absolutely the same thing. Either deciding in advance with this formula or doing everything until the end and then choosing the better precision is basically two different ways to achieve the same thing, okay? In our numerical example that we are going to see in a few minutes, I'm going to do everything to the end using both methods, so you can see both methods working and how they, in my example, produce similar yet different results. So before we go into the example, after you project the errors either with mean per unit or ratio estimation, you need to calculate precision. Why? Because no one can take a decision about the existence of material error in a population, at least under a statistical approach, without knowing the precision, because the precision is the base for calculating the upper error limit. So how to do it? There's a formula. Again, you can use Excel templates. Some audit authorities have developed their own. What is important is that you need to know what to feed in the templates, and there is no doubt. So first of all, for calculating precision, you have a formula if you are estimating with mean per unit estimation, and you have another formula if you are using ratio estimation. Of course, that would not even be necessary to say. If you have two estimation methods, probably they also have two different ways to calculate the precision. Let's see how we do it for mean per unit estimation. What do we need to feed in to calculate precision? The population size, capital N, which is nothing more than the same population size that you have used here for sample size calculation. It's basically the same. How many operations or whatever are my sampling units do I have in the population? Other example. Or other parameter, Z. Again, no doubt. Z that I'm going to use here to calculate precision is the same Z that I have used here for sample size calculation. If I'm working with a 70% confidence level, for instance, Z is 1.3036. What else? here in the denominator, I have the square root of the sample size. Well, sample size, no doubt, it's the sample size that I have used. In my previous example, it was either 40 or 36, because after the 40, it was fine-tuned. So it's a sample size that I have used for my audit. Finally, what is new here in this calculation of precision? The standard deviation of the error amounts. The standard deviation of the error amounts has to be calculated typically in Excel, with an Excel formula. But there is a very important difference between this standard deviation and one that you have used here for sample size calculation. And by this moment, I expect that this is absolutely crystal clear for any of you. So it's a good test if you are really getting it, because of course, this standard deviation that I have used here is an approximation based on historical data or pilot samples or whatever, because I have not yet done the audit, so I don't have a sample. But after the sample is selected and audited, now I have the sample data, and with the sample data, I can calculate this standard deviation of errors, now the real one from the sample that I have audited, and based on this specific formula, I will calculate a certain level of precision, okay? Does not matter. What is important at this moment is that you just understand what are the parameters that are needed to calculate this. In ratio estimation, we have a very similar, but yet slightly different formula. So a big part of the formula is the same. It also depends on the population size, the sample size. The only thing that is here different is the standard deviation. Many of you probably in your own audit authorities, you already have an Excel template where you can calculate this transformed standard deviation. Basically, we can prove that the standard deviation for the ratio estimation does no longer depend on the error amounts, but depends on a transformed version of the error amounts that we decided to call it the Q values. It does not matter. In fact, the interpretation of the Q values, what is important is that we have a way to calculate the Q value. It's the error minus the error rate multiplied by the book value. Let's say for this seminar, it does not matter the reason for this. We just know that if you calculate these Q values, which are the transformed errors, and then we calculate the standard deviation of these Q values, I can get the precision for ratio estimation. At the end, what happens? I have the projected error and the precision. And for any sampling method, the idea is exactly the same. If I multiply, if I sum the projected error and the precision, I get the upper error limit. It's always the same thing. And then my final job is to compare both the projected error and the upper error limit with materiality threshold. If they are above, we conclude population contains material errors. If they are both below, we conclude the population does not contain material error. If one is below and the other one is above, results are not conclusive, and we have to do some kind of additional analysis work or whatever in order to make them conclusive. Yes, I can repeat Francesco, I can repeat the formula. So let's go back. Start with this one. So big parts of the parameters are the same that we have already seen for sample size calculation. Capital N is population size. Population size is the number of operations in the population. Z is the same value that we have used coming from that table of the Z values from the normal distribution. N is the sample size. How many operations have I audited in my sample? And the only, not completely new, but slightly new thing here is the standard deviation. This standard deviation has the same meaning as before. It's a measure of variability of the errors, but it's not the same value that I have used here for sample size calculation, for the reason, because for when calculating sample size, I have not yet done the audit, and I can only rely on auxiliary information or historical data. And now that I have done the audit, imagine that I have 36 operations in my sample for which I have a list of possible errors. either 0 or non-zero. And you can go to the Excel file where you have these 36 operations, as I'm going to show you in the numerical example, and you can calculate the real standard deviation of the errors from the sample. In what regards ratio estimation, most of the parameters are exactly the same, with the exception of this standard deviation that is no longer the standard deviation of the error amounts, but is a standard deviation of a transformed error that, as we are going to see in numerical example how to do it, but basically it's always obtained by subtract from the error amount, subtract the multiplication between the book value and the error rate. Okay, Francesco? Okay, upper error limit compare with materiality threshold, and we take our decision. So before we go for a realistic numerical example, any comments or questions regarding the method itself? Okay, so let's see. Imagine that we have this, a population with 3,852 operations with a book value of whatever, 3.2 million euros. We are going to use, imagine this is, let's say, a category 3 system. So we are going to use a confidence level of 80%. And this audit authority took a pilot sample of 20 operations, okay? I have copied paste into this slide a part of the Excel sheet with the results of the 20 operations that are in the pilot sample. If you see, the first operation is in line 2 and the last one in line 21. So we have 20 operations in the pilot sample. Now, based on our present rules, we always suggest that you take the pilot sample with 30, but let's imagine that we have used the 20. And we have audited these 20 operations, and here I have the results on column D. So on column D, I have the errors that we have found in the audit. For first operation, 0 error, then 56,000, then 200 something, then 0, 0, 0. So it's a typical pattern that we see in our audits. Now, for sample size calculation, what do we need? Population size, how much is it? 3,852. We need Z. How much is Z? Well, if I'm working with a confidence level of 80, Z is 1.282. Just copy it from the table. How much is the tolerable error? Well, tolerable error is simple. It's 2% of the expenditure. How much is the expenditure? It's known. It's the expenditure declared to the Commission, 3.2 million euros. Now, the two most problematic parameters, standard deviation of errors. This one I don't know, but I can use the pilot sample in order to try to approximately as accurately as possible. So I just went to my pilot sample of 20. I have used this Excel function that many of you may know, stdev.s, which is a function that automatically calculates the standard deviation. I have indicated to this function this range from D2 to D21, the 20 error amounts, and the function gave me back 62,194 euros. It's done. It's at this moment, based on the pilot sample, my best guess about this standard deviation. Regarding the anticipated error, also this audit authority has used the pilot sample, so we have calculated an error rate. The sum of the errors in the sample, which is with the sum function, of course, which is 348,000, times the sum of the book values, which is 50 million, gave me an error rate of 0.7%. So anticipated error is basically 0.7% of the total declared expenditure. And this is done. So population size, Z, standard deviation coming from the pilot sample, 2% of the expenditure and 0.7% of the expenditure, and gave me a sample of 55. Because we have already done a pilot sample of 20, we are going to profit from the pilot sample, of course. This means that we have to audit 35 additional operations in order to do our job. Here in the right part of the slide, I have copied again the worksheet with the results of the 55 audited operations. So the first 20 are the ones coming from the pilot sample, and the additionally 35 are the additional ones. Due to save some space, if you see in the between, I have omitted it several lines, but you can see that this ranges from line 2 to line 56, which means that in fact I should have there 55, the results of the audit of 55 operations. Okay. How to project the errors? Either we use mean per unit or ratio estimation. Let me show you how to use it. Mean per unit estimation. Sum of the errors in the sample. So I just went here and summed all the errors. They are in column D. I summed all the errors, and the total error in the sample is 546 or 47,000 euros. I divide by the sample size. This ratio is the average error in the sample, and I multiply by the population size, which is 3,852 operations. So my projected error is 38 million euros, and it's done. This is the projected error from mean per unit estimation. But just for the sake of my numerical example, let's do everything using both methods. If I use ratio estimation, how do I do it? Well, I still sum all the errors in the sample, but instead of dividing by the sample size, I divide by the audited expenditure. Where is it? Well, it's the sum of the 55 book values, and the sum of the 55 book values gave me 52 million euros. So here it is. Total error in the sample, audited expenditure, times the total book value of the population. It's 3.2 thousand million, and this gives me a projected error of 33.6 million euros. Now, is it the same value as for mean per unit estimation? No. Would we expect to have the same value? Of course not. We have two estimation methods. We expect them to produce different results. Which is the best one? I don't know yet. Either I have to apply that condition that I showed you, or I have to calculate precision for both methods, and by the end of the day, choose the one that has better precision. Do they produce the same result? No. Do they produce very different results? Also not. If I divide this projected error amount by the total declared expenditure, how do I get? The projected error rate using mean per unit estimation is 1.2%, and using ratio estimation is roughly 1.1%. Well, very much in the same neighborhood, either 1.1 or 1.2%. So the two methods are different, produce slightly different results, but they are not, in this case, at least dramatically different. But anyway, we should rely our decisions on the most precise one. So let's calculate precision for most of them. And very important question now that I see, are the two methods of error projection also used in non-statistical sampling the same way? Exactly in the same way. And we have to do the same check, but there is only one difference. While in statistical sampling, you can save your decision to the end, because under statistical sampling, you can calculate precision for most methods. Under non-statistical sampling, because we do not calculate precision, we don't have a way based on precision to check what is the best method. And because of that, under non-statistical sampling, the choice between one method or the other is based on this condition here, because we are not going to calculate precision, but it's basically the same thing. You verify the condition. If the condition is verified over the sample, we use ratio estimation. Otherwise, you use mean per unit estimation. Okay. For the new programming period, post-2020, we have a simplified approach. You can still use both methods, but there will be some differences, but I will save that for tomorrow. Now, done. Let's, for the sake of the example, and although we know that the two projected error rates are quite similar, let's just, for the sake of the example, use calculate precision in both cases. So again, parameters are known, population size, the same Z that I have used before, Sample size is 55. What about the standard deviation of the error amount? Standard deviation of the error amount, I will get them from the sample. I go to this Excel sheet and I calculate the same function stdev over the 55 errors. And this function gave me a standard deviation of 56,000 euros. Here it is. It was so easy as calculating this with this Excel function over this range of 55 items, gave me this 56,000 euros. I don't care about the value itself. I just care that inserted in some formula, this will give me the precision, which is 37.6 million euros. What about ratio estimation? Well, the formula itself is quite the same until here, but the standard deviation is no longer the standard deviation of the error amounts, but is the standard deviation of the Q values. How to do it? Well, in Excel, I have created a new column called the Q value. How is it? Remember, please, error minus error rate times the book value. I will simplify for the first operation in the sample. For the first operation, how much is the error? Column D, the error was 0. Okay, I put here 0. How much is the error rate? Well, the error rate I have already calculated before. The error rate was here. 1.05. Or if you want, I have calculated also here 546,000 euros divided by 52 million. It gives me this 1.05%. So I put here the error rate calculated in this ratio times the book value of that operation. How much is the book value of the operation? Operation 1, book value is here, 1,368 something. Okay, it's done. I calculate the value. It's even a negative value. I don't care about interpretation. It's here, minus 7.016. And then I just copy paste down for the 55 operations. What do I get from this? A new series of 55 values that are no longer equal to the original errors, but are a kind of transformed version of the original values. And then what do? I use the same Excel function stdev.s, but instead of being applied over the column D of the error amounts, I will apply over the column F of the transformed errors. And if you see here in line 58, the standard deviation of these 55 values gave me 58,000 euros. Okay, I don't care. I just put, the 58,000 euros here in the formula and gives me the precision. It's done. Now I have the precision for mean per unit, 37.6 million euros, and the precision for ratio estimation, 38.9 million euros. Are they very different? Not at all. They are very similar, which means basically that the quality in this particular example, the quality of mean per unit or ratio estimation is relatively indifferent. We could use one or the other. But to do the job by the book correctly done, we should rely our decisions, our opinions based on the method that offers us better precision. What is the method that is offering me better precision? This one gives me a precision of 38.9 million. This one gives me a precision of 37.6. Although very similar, this one is slightly better. The smaller, the better. The precision, it means that I expect this projection to be closer to the truth than the other one. So basically, I would rely from now on all my analysis on mean per unit estimation because it's a slightly better method. But let's say in this particular example, this does not make a difference. The conclusions would be exactly the same. But as some of you may know, in real life, we also get situations where the two methods can be quite different. And in fact, it is important to rely our decisions on the best method. So based on this, here we have the upper error limit calculated. Now, just for the sake of my numerical example, I have calculated it for both methods. So projected error and plus the precision under mean per unit estimation, the projected error plus the precision under ratio estimation. Again, very similar results. And by the way, detail that is a feature of this data set that I have used to show you this example. I have created here a situation where results would be inconclusive. So the projected error was below materiality and the upper error limit was above materiality. To be honest, this is why I would like to create a situation of inconclusive results. Why are results inconclusive if everything has been done correctly and by the book? Just because we have used, as I said many times this morning, an unrealistic anticipated error. And follow me, ladies and gentlemen. What is the amount of error in this population? I don't know the exact value, but see, 1.2%, 1.1%. So it's in this neighborhood, 1.1 or 1.2%. How much have I used for sample size calculation here? For sample size calculation, I have used an anticipated error of 0.7%. Will I get conclusive results? Of course not. Why? Follow me. If I'm using an anticipated error of 0.7%, it means that I'm asking to this system to offer me a precision of how much? The precision is 2 minus 0.7, so it's 1.3%. So what I'm asking to this sampling methodology is to give me a precision of 1.3%. But what happens by the end? I have found that I have been too much optimistic and that my projected error is more in the neighborhood of 1.2 or 1.1%. But what happens? Well, with a precision of 1.3 that I have asked, and by the way, it worked well. The final sample has a precision in the range of what I have asked. I will expect an upper error limit of 2.5. So there is no doubt. If I ask the system to give me a precision of 1.3, the system gives me what I have asked perfectly. It has worked, but I have asked wrongly. I have not asked what I need. I have asked more than I need, and this means that it's almost a fatality that by the end of the audit we will have an upper error limit in this range of 2.5%, which means inconclusive results. And this is always what happens if we have unrealistic anticipated errors. By the way, is it possible that we have an unrealistic anticipated error and then by the end of the audit results are conclusive? Of course, it may happen, and it happens sometimes, just because we are lucky, because although we have been too optimistic in terms of anticipated error, there are other things that have compensated this fact, and by the end of the day, results are still conclusive. But let's say this is the exception, not the rule. The rule is that if I ask too large precision, almost surely the results by the end of the audit will be inconclusive, as in this case. Everything else was perfect. Everything else in this example has been perfectly done, with the exception of this little bit or very much optimistic anticipated error. Okay, and this is all about this numerical example for simple random sampling. Now a little bit of stop for any comments or questions. No questions? Sure.
Very well. So doing this, let me tell you something about multi-unit sampling. Again, it's a sampling method like simple random sampling, is probably or by far the most well-known method among the methods that are available in the world of audit for substantive testing. Fortunately, the strategy that I have used to show you simple random sampling can also be applied in MUS. Everything is very similar. We have a formula for sample size calculation. We have a formula for projecting the errors, everything else. But of course, the technical details are slightly different. So first of all, please remember yourselves that Monetary unit sampling is a method that we use when, first of all, in a situation where we know that we are going to select the operations or whatever are the population items with probability proportional to expenditure, which means that my sample will be full of high value items and it will have too few low value items. So under MUS, the sample is very much distorted in relation to the population. But this distortion that MUS introduces in the sample is not a problem at all, because this distortion will then later on be compensated in the projection device. The projection formulas will take into consideration this distortion in the sample. And usually this distortion is a good thing. If the conditions for MUS hold, it's true that this method will produce better results, more precise results. And this is situations where, I repeat again, we see high variability in terms of operations expenditure, and we also expect positive association, proportionality between errors and expenditure. When this happens, we can assure you that MUS tends to produce smaller sample sizes than simple random sampling for the same level of precision, and or can improve the precision in comparison with simple random sampling. So step by step, what do we need to know in order to calculate the sample size for MUS? Very much the same parameters with some adaptations. You can look into this formula and see what are the common things. Z is the same thing as before, is a parameter from the normal distribution associated with our confidence level, and our confidence level itself is the result of our evaluation about the reliability of the control system. Now, instead of capital N, which is the population size, now we use BV, which represents the population book value, I mean the total declared expenditure. Then the tolerable error is the same thing as before. Tolerable error is 2% of the expenditure, no doubt. What about the two uncertain parameters, the standard deviation and the anticipated error? Well, regarding the anticipated error, no doubt, is exactly the same thing as for simple random sampling. It's the error that we expect to find by the end of the audit based on historical data, pilot samples, professional judgment, auxiliary information. Regarding the error, the standard deviation of the errors, it's also based on the same sources of information as before, pilot samples, historical data, but with, again, a small but yet very important difference. This standard deviation that feeds in the formula for sample size calculation under MUS is no longer the standard deviation of the error amounts, but it's now the standard deviation of the error rates. That's why I put an index R instead of an index E, okay? So it's very simple. It's calculated in Excel with the same function stdev.s, but instead calculating it over the column of the error amounts, I calculate it over the column of the error rates. Let me check a question here. In the column errors, in case of subsampling, we have to put projected error to the operation. Exactly. If you are using subsampling, you can still apply these formulas, but all the parameters relate to the operation within which you are selecting the subsample. So the size is the size of the operation, the book value is the book value of the operation, and so on. Again, not going to deal with that today, but maybe I don't know if tomorrow we can deal with that. Now, as before, if you do not rely on historical data, you can use a pilot sample, and as before, the pilot sample should be done with a sample size of 30 is our suggestion. And now, ladies and gentlemen, let me tell you something that many of you may feel. I hope you agree with me with this. I probably remember that several years ago, when I started working with the Commission, I found that many audit authorities were a little bit reluctant in using pilot samples under MUS. It was okay for simple random sampling, but not so much for MUS. And why was that the case? Because MUS tends to select the larger operations. If you select a pilot sample of 30, this means that 30 very large operations, typically the larger operations in the population, will be selected to the sample, which means that there is a lot of audit work to audit a pilot sample under MUS. While this was true in the past, I believe that is no longer true. And now the audit authorities do not feel this so much or don't feel this at all, because most of the audit authorities are using subsampling. I mean, once they select an operation, they realize that they do not need to audit the full expenditure of the operation. They will just audit a subsample of invoices, let's say. And because of this, these days, auditing a large operation or a small operation is to some extent basically the same thing. And this means that no longer we can say that auditing a pilot sample in MUS gives you much more work than auditing a pilot sample under simple random sampling. Okay, so please do not forget this possibility that although technically we don't have time today to deal with subsampling, but this possibility that you can always use subsampling either within the pilot samples or within the final sample. Now, under MUS, the selection of the sample itself has some particularities, and I really need your attention to this. In standard MUS, before selecting the sample, you have to do some things. Let me open here an empty slide so I can explain to you this. So the idea is the following. In MUS, before selecting the sample and remembering that the sample is selected with probability proportional to expenditure, you have to manually, or using some software that will do that for you, but manually separate from the population what we call in MUS the high value items. And what is the cutoff value for determining a high value item in MUS? The cutoff value is the ratio between the book value and the planned sample size. So you calculate this ratio, and any operation in the population whose individual book value is larger than this cutoff has to be taken away from the file from which you select the sample, and it will be placed in a special file, a special, let's call it bag, of what we call an exhaustive stratum, a stratum where 100% of the operations will be audited. So the idea is the following. You have the population here. You have here the threshold, which is book value divided by the sample size. All the operations in the population that fall above this threshold, they all have to be audited. They are placed in this special high value exhaustive stratum. And for the remaining of the population, the ones that are below the threshold, in this case, you are going to select a sample under the MUS rules, and you are only going to audit the operations in the sample. So in MUS, basically, you have to separate the population in two groups, the so-called high value items and what I could call the low value items, or the sampling part of the population. So if you have a global sample size N, let me call this size here NE, which is the size of the exhaustive stratum, and this size of the sample NS. Okay, so the number of items that you are going to have available to audit in the sampling stratum is the planned sample size minus the number of items that by chance have fallen into the high value group. Okay, and you have now these two groups in the population, the exhaustive and the non-exhaustive group. Now, once you know that these ones you have to audit them all,
for these ones, instead of auditing them all, you just need to audit a sample, and you are going to select the sample with probability proportional to expenditure. And for doing this, you are going to use typically a systematic selection procedure, where you are going to select the operations in the file with steps of equal range, and the range is called sampling interval, is basically the book value of this sampling group of the stratum of the population divided by the sample size of this sampling group of the population. And I will show you in practice, when I show you the numerical example, I will show you in practice how to put in, how to do this systematic selection in Excel. It's absolutely simple to do it in Excel, but many of you will also use specific software applications to do this. Okay. Now, there is here a trick that many of you know, but it's extremely important to stress, because we have seen errors in this regard. Once you reach this point and you calculate this sampling interval, it may happen that you still have some items in this population whose expenditure is larger than the sampling interval. So it may happen that, imagine that the original cutoff was 50 million euros. And now the sampling interval is 48 million euros. If by any chance you have here an operation whose book value is 49 million euros, what does it mean? It means that has not been moved yet to the high value stratum because it was below the threshold of 50, but now 59 million euros is larger than the sampling interval. All the operations that remain in the population with a book value larger than the sampling interval, they have to be manually added to the high value stratum. Okay. So again, if you have another one, you just move that one up to the high value stratum, and you have to recalculate again the sampling interval, because if you have taken one operation from the population, the book value of the population has changed, has gone down, because I have taken one away. Now, as maybe also some of you have noticed this in real life, after moving this new item or new items to the high value stratum, and after recalculating the sampling interval, it still may happen that now you still have another item that is above the new sampling interval. Now, imagine that the new sampling interval is no longer 48, but 47 million euros. If by any chance you have in the population an operation whose value is 47.5 million euros, this means that has not yet been moved to the high value stratum because it was below the threshold, but now it has a book value larger than the new sampling interval, and we have to move it again. So you have to repeat this process until no further operations exist in the sampling part of the population with book value larger than the sampling interval. To be honest, I think many of you know that very often we solve this with just 1 or 2 iterations, but there have been cases where you have to perform 3 or 4 iterations in order to move them up. If any of you have ever needed to do more than 3 or 4 iterations, please let us know in the chat, because I would say that is very, very unlikely to happen. That is very seldomly would happen. So by the end of this process, we reach this iterative process, we reach a situation where we have a certain exhaustive group where all the operations are going to be audited, and a sampling group where we are going to select the sample. Okay. Now let's imagine the sample has been selected. During the numerical example, I will show you at least once the selection of an MUS sample. But now let's imagine the sample has been selected. How do you project the errors into the population after the audit? Well, the projection is no longer equal as in simple random sampling, is no longer based on mean per unit estimation or ratio estimation. In each sampling method, the way to project the errors is different. So how to project the errors under MUS? First of all, I think without surprise to anyone, I could say, if my sample is composed by two parts, this part here, that it was an exhaustive observation, and this part here that was based on sampling, probably the projection is done differently to this part and to this part, of course. So let's start with the high value items. How do I project the errors for this high value group of the population? To be honest, no projection is needed. What projection? I have audited them all. There is no projection to perform. For the high value group, because it's a census, it's an exhaustive audit, I just need to sum the errors that I have found in the audit, and that's it. This is the error of the exhaustive part of the population, of the high value stratum of the population. No projection is needed. Now, let's move down to the sampling part of the population. Oh, in the low value stratum of the population, it's different. I have to find a way to project the errors from this sample here into the population. How? Using a formula that I'm going to decode here, but it's extremely easy to understand. For each unit in the sample, I will calculate the error rate. What is the error rate? Well, of course, it's the ratio between the error of that operation and the expenditure of that operation. I sum all these error rates over all units in the sample. Then I multiply the previous result by the book value of this low value stratum, and then I divide this result by the sample size of this non-exhaustive stratum. Or maybe said in a more simple and eloquent language, that's it. Look here, sum of the error rates multiplied by the ratio between the book value and the sample size, that, by the way, is the sampling interval. So in other words, the projection is just the sampling interval times the sum of the error rates, okay? And that's it. Based on this, I have projected the errors from the sample into this part of the population. Now, how much is the total projected error? Total projected error, again, without surprise, is the sum between the error that I have found in the high value group and the error that I have projected in the low value group. And this is the total projected error for the population. After I have projected the errors, and as always, I have to calculate precision. Well, to calculate precision, I just need to know which parameters to input. I need to use Z. Again, Z is exactly the same Z that I have used here for sample size calculation. Here, the same Z associated with the quality of the control system. What do I also need to calculate precision? Let's see, book value of the sampling part of the population, sample size of the sample part of the population, and the standard deviation of the error rates. Where do I get the standard deviation of the error rates? From the sample. I go to my sample, I calculate the standard deviation using the same function as in the previous example, stdev.s, and I get the standard deviation and I do the calculation. Just a very important remark, please don't forget this. Sometimes someone forgets. All this calculation here is performed only using the part of the sample that corresponds to the low value stratum, okay? To calculate the precision, you don't use the high value part of the population. You just use the sample from the low value part of the population. Why? For reasons that you understand. The high value part of the population is not contributing to precision at all. It does not contribute with any uncertainty because I have audited the whole list of operations. There is no doubt about it. The only uncertainty comes from the selection of this sample here, and that because of this, all the calculations in precision are exclusively based on data coming from the part of the sample that corresponds to the low value items of the population. Once it is calculated, as usual, the upper error limit is the projection plus the precision, and as usual, we will compare the projected error and the upper error limit with materiality threshold, and either we conclude population contains material error or no material error, or results are not conclusive, okay? And that's it. everything about standard MUS in a glance. And before I move on to a numerical example, I would like to do another stop to ask you about any further questions or comments. Guys, let's do a 15 minutes break now. And then we'll see the example after the break. Otherwise, then the second part of the afternoon will be much smaller than the first one. Okay, so 15 minutes. Let's resume by 4:20. Okay, guys, welcome back. Before we resume with the example, I see another question in the chat. In fact, this is not very much related with what we are talking about, but let's find it. The example is, we have a payment claim of 1,000 euros. So let's imagine the sampling unit is a payment claim. And regarding public procurement checks, you found that you should apply a financial correction of 25%. And also during the audit, we find 100 euros of error. So the question is, how much should be, so correct me if I'm not interpreting the question well, how much should be the error that should be attributed to this sampling unit before projecting this error to the population? Again, this is a more complex case that we should see with more care, and what I'm going to answer at this moment does not commit the opinion of the Commission regarding this, but let's say what in principle makes sense. You put two options. One is multiply to 25% by the expenditure of this payment claim and adding the 100 euros of error. That would give you 350. Another option would be to take this error from the total expenditure of the payment claim and multiply by 25 and gives you 225. So I would say, in principle, none of these two methods is absolutely correct. I would say the second method, it's okay. You should apply the 25% to the expenditure of the payment claim after taking away the amount of error that you have found. So this part is okay, 225, but you have not written that, but maybe it's what you mean. But also you have to add the 100 euros of error. So in principle, but we should check with more care, but in principle, the amount of error that you should attribute to this payment claim should be 325. Okay, so the error found plus the financial correction that is applied to the remaining expenditure of this payment claim. I don't know if it's correct, Yolita. Yes, thank you. Okay, I see that you agree. Thanks. So let's go to the numerical example under MUS. So we have this population of expenditure. Let's in this example use a 90% confidence level, 3,800 something operations, 4.2 million euros of expenditure. Let's calculate the sample size as usual. For that, you are going to use, for the unknown parameters, we are going to use data from the previous year. And from the previous year, we have 50 operations in our sample. These five high-value operations that are in this table, and additionally 45 that are in this copy table here. And basically from the previous year, one of the things that we need is the standard deviation of the error rate. So basically use the same function in Excel, stdev.s, The only thing is that, contrary to the previous example, instead of calculating this over the error amounts, which is column D, I'm going to calculate the standard deviation over the error rates, which is column E. So error rate is just the error amount D divided by the book value in column B. And based on this, the standard deviation, the historical standard deviation of error rates was 0.085. That's it. So let's calculate the sample size. Z, this is the Z associated with 90% confidence level, book value of the population, it's known. This standard deviation is the one that is coming from our historical data. This is 2%, 83 or 84 million is 2% of the book value. And in this case, I don't know what is the source for this, but let's say the audit authority considered an anticipated error of 0.4%. So anticipated error rate of 0.4%, so 0.4% of the total expenditure is 16.8 million euros. This gives a sample size of 77. So first thing is to separate the high value items from the low value items. And for that, we need to calculate this ratio, the total book value of the population divided by the sample size, 54.6 million euros, which means that any operation in this population whose individual book value is larger than 54.6 million euros will be moved to this high value stratum. By the way, in my example, let's imagine that I have found 8 operations with book value larger than this threshold, with the total book value among these 8 operations of 786 or 787 million euros. Now, let's go to the remaining population. So what is my original sample size? 77 minus the 8 units that have fallen into the high value stratum. I have now 69 items in the sampling stratum. Now, how to calculate the sampling interval? Book value of the sampling stratum, which is the total book value of the population minus the expenditure of the 8 high value items that I have moved away, divided by the sample size, and my sampling interval is 49.5 million euros. Now, please notice this sampling interval is, of course, always smaller than the original threshold, 55 million euros. So imagine that by any chance you still have in your population an operation whose book value is above this 49 million, but below this 54 million, again, you have in this iterative process to manually move it to the high value stratum. In my example, I don't have any additional operation in the population with a book value larger than 49 million euros. So I didn't need to move anything else. So my final high value stratum continues to be constituted by these 8 operations, okay? Now, how do I select the sample? So for the 8, it's easy. We have to audit them all, to audit the 8. For the remaining population, how do I select a sample of 69 operations? Well, I use a systematic procedure. By the way, I don't know, maybe some of you are used to do this in Excel, others not, but I will show you for me, the easiest way to do this in Excel. If you have your Excel file with all the operations in the population, I have here the ID of the operation, I have here the book value, and I find it useful to create a third column that is the accumulated book value. What is the accumulated book value? Well, it's very easy. For the first operation is the book value of the operation. For the second is the sum of the book values of the first 2. For the third is the sum of the book values of the 3. For the fourth is the sum of the book values of the first 4, and so on, so on. So for the last operation is equal to the total book value of the population. Yes, Shams. If you move 49,000, then you will get another interval until necessary. As I asked you before, I ask your colleagues if someone has found in their lives a situation where they have to perform this more than 3 or 4 times. Nobody answered, so I assume that nobody has ever seen a situation where this would happen. This may be because lack of experience or because you have never really seen it. So I would say that in majority of the cases, I repeat what I told you before the break. Either usually one or two times, maybe sometimes a little more, but usually not more than that. But the answer is, the formal answer is until necessary, until no further items need to be moved up. Okay, done. How do I select the sample? Look, guys, how easy. Yes, one time may be okay. If in this case it was, in my example, it was just one time. I don't have any additional items with a book value larger than 49 million. So nothing needs to be done. But if I still keep having items with book value larger than the sampling interval, I need to keep moving them up until no further items have book value larger than the interval. Yes, exactly. Now, imagine that I want to select this sample of 69 items. Now, how do I start the process? Generating a random number. This is probabilistic sampling. I always need to generate at least one random number. And the first random number that we generate is a random number between 1 and the sampling interval. So please remember that my sampling interval is around 49 million euros. So you go to Excel or any place and you generate a random number between 1 and 49 million, okay? And now, please imagine that I have generated 22 million euros, or is my random number, okay? So what is the first item to be selected to the sample? The first item to be selected to the sample is the first operation in my file whose accumulated book value is equal or larger my starting point. So let's see. My starting point, please remember, is 22 million. So what is the accumulated book value of the first item in the file? 10 million. Is 10 million larger than 22 million? No. If not, this item does not go into the sample. Second item in the population, 33 million. Is 33 larger than 22? Yes. Oh, if yes, then this item is selected to the sample. Now I already have my first item into the sample. Once I have an item in the sample, I have to move on, to move my selection point. How? By adding to the starting point the sampling interval. The idea of MUS is to advance in the file with steps of equal range, being the range, the sampling interval. So if I add the sampling interval of 49 million to the starting point, I get 71 million. So the second item to be selected to the sample is the item whose book value, first item whose book value is equal or larger 71 million. 66 is larger than 71. No, so it does not go into the sample. 100 is larger than 71. Yes, so this one goes into the sample. Once I select another one, I have to add again 49 million, and I get a new value. And then again, I will keep doing this. Compare the book value with this reference value. If it is larger, it's selected to the sample, otherwise not. And I keep advancing into the file, operation by operation, saying yes, no, this is selected, this is not selected, until I have selected my 69 operations. When you have selected the 69 operations, you stop, and you know that you have selected your sample with probability proportional to expenditure, and of course your sample will have a lot of high value items and a less representation of a smaller representation of low value items. But selecting an MUS sample is so simple as doing this in Excel. We don't even need any specific software to do so. So after this process, I have selected a sample of 77 operations, 8 high-value operations that are exhaustively audited, and 69 low-value operations that are audited through sampling. Now, how to project the errors? For the 8 high-value operations, there is no projection. I just sum the errors that I find. By the way, I have found errors over 3 out of the 8 high-value items, and the total error was 7.6 million euros. It's done. There is no projection. For the remaining 69 operations, I have to project the error from the sample to the population using that formula that we have seen before the break, sum of the error weights times the sampling interval. Let's do it. This copy of this Excel file here has a list of the 69 operations in the sampling stratum. In column E, I have the error rates, and I have just in line 71, I have just summed them, and the sum of these error rates is 1.096. I don't care about the value. I just copy this value, 1096, and I multiply by the sampling interval, and I get the projection. My projected error for the sampling part of the population is 54 million euros. What is now the total projected error? Well, very simply, the total projected error is the error that you have found in the exhaustive stratum plus the error that you have projected in the sampling stratum, and the total projected error amount is 61.8 million, or if you divide by the expenditure, roughly 1.5%. And it's done. Now, what is missing? The precision. How to calculate the precision, just to feed in the values of the parameters. So that is 1645 as for sample size population. This is the book value of the non-exhaustive stratum. The sample size is 69, and the standard deviation of the error weights. Well, in what regards the standard deviation of the error weights, I just go to my Excel file over these 69 items, and I calculate my usual function stdev.s, and I got a standard deviation of 0.09. It's done. I input here 0.09, and I got this precision of 60.8 million euros, and it's done. As always, the upper error limit is the projected error plus the precision, 122 or 23 million euros. I compare them both with materiality threshold, and again, in this example, the results were not conclusive just because. The only reason is that the error weight is in the neighborhood of 1.5%, and in this case, this audit authority has used I don't know even with which source, but it has used an anticipated error rate of 0.4%. So with anticipated error rate of 0.4%, there is no way we would get conclusive results, because as again, the planned precision is 2 minus 0.4, which is 1.6. If I'm asking for a precision of 1.6 for a projected error in the neighborhood of 1.5, 1.6, it means that this upper error limit will be very high, above 3% or so, which means that, of course, results in this case would be very much inconclusive. But this was, again, the only reason was a bad or a too much optimistic approximation of the okay. And this is it about our example. Any final comments or questions? Anything about the numerical example? Let's do like this, guys. I'm going to cover stratified MUS in a very, let's say, fast and less technical way, so we can save some time to still have some time for non-statistical sampling, which is, of course, very important. Questions? What was the 69 in the formula? 69 was the sample size, you remember? Here it is. The formula, see here, sample size, NS, and if you remember from the example, the sample size was 69. Let's go back just for us to remind us that a sample of 69 operations was selected using that procedure that I showed you with the starting point, with the steps of equal interval and so on. Good. Anything else? So let me tell you something about certified multivariate sampling. Just give me 10 seconds to be. Good news. There is almost nothing to learn when doing a certification. Why? Because doing a certified multi-unit sampling procedure is the same thing as doing a multi-unit sampling procedure as many times as stratum. This methodology was designed in such a way that whatever you do within each stratum is just a standard MUS approach that you have just learned. So in practical terms, there is not really much to learn. So you are going to divide the population into populations called stratum, and you take an independent sample from each stratum. Example, you have this population here that is a group of 2 programs, program 1 and program 2. And you may decide that you want, for the reasons that we have longly discussed in the morning, to stratify this population by the 2 programs. No problem. After you decide to stratify by program, what you are going to do among the expenditure of program 1 is just a normal MUS, and among the expenditure of program 2, a normal MUS, and then you just have to join them together. So really, there's not much to understand. By the way, a very important point, under MUS, you can use any stratification criteria as the ones we have discussed in the morning, programs, regions, intermediate bodies, risk of operation, so on. There is only one stratification criteria that you never use under MUS, which is the stratification by classes of expenditure. There is a stratification that is very popular under simple random sampling to stratify the population between high value, medium value, and low value items. This is pointless with MUS. Why? Because MUS is already selecting the items with probability proportional to expenditure. So in a way, we can say that MUS is already implementing an implicit stratification. So doing any additional stratification based on expenditure would be completely redundant and would not bring any gain in the context of MUS. Okay, it's just not stratified by expenditure, but everything else is possible. Now, the idea is very simple. After you decide to stratify by program, you take program 1, you forget program 2, and you do an MUS in program 1, a high value group and a sampling group. Then you go to program 2 and you do the same thing. Forget program 1. Here you take a MUS sample with an exhaustive group and a sampling group. And then how many pieces of information do you have to project to the population? Well, for 1 high value group here, 1 sample here, 1 high value group here, and 1 sample here. So in a certified MUS where I have 2 stratum, I have 4 components in my population, 2 times 2. If I would have 3 stratum, no problem, I would have 6 components, 2 times 3. And if I would have 4 stratum, 8 components. And by the end of the day, doing this certified MUS is just summing the errors that you find in the exhaustive stratum and projecting individually and independently the errors from the sampling parts, and by the end summing all of them, and it's done. So there's nothing to learn here besides what we have just learned. Does it mean that, for example, mean of certified? A very good question. No, not at all. the minimum sample size of 30 applies to the whole population. Per stratum, we don't apply this rule. So what is the minimum sample size per stratum? The minimum sample size per stratum is just defined by practical reasons because we need to calculate standard deviations, and it's impossible to calculate standard deviations with less than 3 to 5 items. So we always recommend the audit authorities that ideally, if possible, never use by stratum sample sizes less than 5, or in the limit, never use sample sizes smaller than 3, okay? 3 is the very minimum for a sample size in one stratum. Now, you calculate the sample size with the formula. Now let's not go into the technical details, so we will lose a lot of time, but the formula is very different, very similar to the standard MUS formula, with the only difference that now the standard deviation, as probably you would expect, is a combined standard deviation from the 3 stratum or the 2 stratum that you are working with. No doubts. The only new thing that you need to learn here, and this is really the only important thing, is that once you have calculated a certain sample size, imagine 50, if you have 2 stratum, you have to allocate this global sample size between the 2 stratum. So how much shall I audit in program 1 and how much shall I audit in program 2, knowing that the very minimum is 3 to 5, but how much shall I audit? Well, there are many sampling strategies to do this. The most well-known way to allocate the sample between stratum, and very straightforward, is to allocate proportionally to expenditure. I mean, the sample size of a certain stratum H is proportional to the expenditure of that stratum divided by the total expenditure of the population. In other words, if a stratum represents 40% of the expenditure of the population, we'll also have 40% of the sample. If a stratum has 70%, we'll have 70% of the sample, and so on. Please don't think this is the only way to allocate the sample. In fact, a few years ago, we have introduced the possibility for the audit authorities to use smarter allocation schemes, and in particular, something that we have called the optimal allocation that was presented in a technical meeting or something like that. So many other different methods are acceptable, but let's say our basic proposal is to do this allocation proportionally to expenditure. Then what we do in each stratum is an MUS. How do I project the errors finally? I sum the errors that I have found in the several exhaustive stratum, and then I project separately the errors that I have found in the sampling stratum. Imagine that I have 2 stratum. Well, the total projected error is equal to the sampling interval of stratum 1 times the sum of the error weights of stratum 1 plus the sampling interval of stratum 2 times the sum of the error weights of stratum 2. I mean, nothing new. You do exactly what you have learned. There's nothing to learn in certified MUS. The only thing you have to remember is, I will do this for program 1, I will do this then for program 2, and if I have a search stratum, I do this for program 3, and so on, as many times as I have stratum, but using exactly the same strategy and the same formulas that we have seen for standard MUS. And then the total projected error, as usual, is the error found in the exhaustive groups plus the error projected in the non-exhaustive groups. And then we have a different formula for precision calculation. But the formula, one thing that you need to understand is what is there. It's again the same thing. It involves the book values of the sampling part of each stratum, the sample sizes of each stratum, and the standard deviation of the error weights of each stratum. So it's basically the same thing that you have seen for standard MUS, but you have to do this again as many times as stratum, and by the end, sum them all. It's the only difference, okay? And then you calculate your error limit, you compare them both with the materiality threshold. So what I propose is the following. Let me skip the numerical example, and let me address with a little bit more care the non-statistical context, okay? in stratified MUS or stratified simple random sampling or stratified approach, this strategy does not allow you to have an audit opinion per stratum. The stratification is just a feature that you introduce in the sampling design in order to improve the precision or to reduce the sample size. But the sample itself is only designed to be representative of the grouped population, of the full population. If you like to have results representative by stratum, for example, by program, if you have a stratification by program, this means that very often you need to do an oversample of the stratum per program of each program in order to guarantee that not only you have results representative of the population, but also representative at stratum level. Sorry, guys, there is a topic in our trainings which is grouping of programs and how can we, in some cases, after grouping a program, have separate audit opinions per program, but we don't have time in this basic training today to cover that, okay? So if you'd like to have an audit opinion per program, you don't group the programs. If you have two programs and you really want, you are sure that you want an audit opinion per program, then you treat this as two separate populations. You plan a sample size for program 1 and you plan a sample size for program 2, and you don't even need to have a global opinion for the group of the two programs. So let's say that there are two extreme situations. One is you know that you want separate audit opinions. So you treat this as two separate populations. You don't even care to group. Another option, you know that you want to group and you don't need opinion per program. In that case, you group them, you can stratify, but your sample is designed to be only representative of the group population. Third option, you want to group, you want to stratify, but you are still like, by the end, to be able to have some conclusions per program in order, for example, something that is very typical. Sometimes you group 10 programs and imagine there are 1 or 2 that have very large errors, and these 2 are contaminating your audit opinion. Globally, you are projecting an error larger than 2%, just because you have 8 programs that are okay and 2 programs that have higher error rates. In this case, you can do some kind of boost oversample of these 2 groups, the group of the 2 programs where you expect to have higher errors and the group of the programs where you expect to have lower errors, to guarantee that your sample is not only representative of the whole population, but also tend to be representative of these 2 subgroups in order for you, if necessary, by the end of the audit, if this is confirmed, to separate these 2 groups and to be able to issue 2 separate audit opinions. And in this case, you can declare that you have a group of 8 programs that does not have material error and a group of 2 or 3 programs that have a material error, okay? But this is the topic for another type of training, but this is the general idea. Okay, again, in certification, you don't need to have opinions per stratum, and you don't need them and you don't want them. If you are sure that you want opinions per program, you don't group them. You work with them separately. Now, non-statistical sampling. As I said before, non-statistical sampling, statistical sampling should be used as a whole. Non-statistical sampling is reserved for situations where the population is small, and to implement a statistical sample would represent a disproportionate effort. But this is something that no auditor would like to use, because by the end of the day, you cannot calculate precision, you cannot control the audit risk, and you don't have any idea about what is the risk of your opinion to be invalid, that you may be declaring, let's say, declaring an unqualified opinion when in fact the declaration of expenditure contains material errors. So we always suggest that these non-statistical sampling should be avoided by grouping programs or by changing the granularity of the sampling units, but there will be many situations in our lives where the population is just too small, even by doing these things, and you find yourself in the situation of having to use, making sense, or at least making sense to use non-statistical sampling. For the ending programming period, the threshold, as I said, is a range between 50 and 150 operations. For the post-2020, it will change, as you are going to see tomorrow, or at least the ones that are tomorrow with us. The final decision always takes into consideration the balance between the cost and the benefit associated with each one of the methods. In cases where exceptionally an audit authority would like to still use non-statistical sampling when you are above 150, imagine that you have a population of 152 operations, and you still consider that the effort associated with statistical sampling is disproportionate, you should, of course, seek commission advice in order to see if the commission considers that this is still possible or not. I already said, but I would like to underline that even under non-statistical sampling, the sample itself has to be selected with a probabilistic method. So either with equal probabilities, as in simple random sampling, or with probability proportional to expenditure, like in MUS. So the selection of the sample completely mimics what we do under statistical sampling. The only difference is that the sample size does not use a formula. So the sample size is determined empirically based on the professional judgment of the auditor, taking into consideration also, of course, the reliability of the control system, and also the precision, as I said, is not calculated. Very important recommendation, when you implement non-statistical sampling, let's say, I think you all agree that non-statistical samples have some risks, have some fragilities, because we cannot control the audit risk. Because of this, we should help as much as possible non-statistical samples to try to increase their quality as much as possible. One of the things that you already all know that you have in your power in order to improve the quality of a non-statistical sample or of any sample is stratification. So if stratification is a good tool to improve the quality of a sample, by all means, it should be applicable in the context also of non-statistical sampling. So we advise that, if possible, consider the stratification of your non-statistical samples. This is a very efficient tool to improve the quality of the projections, and it's very recommendable in this context. One of the ways to stratify a non-statistical sample is to stratify by level of expenditure. By the way, any other stratification is possible by program, by risk, whatever you would like to use, but it's very popular in non-statistical samples to stratify by expenditure. Please consider that because the sample sizes are usually small, very often we just consider to stratum, let's say the high value and the low value items. And for this, please consider that the cutoff between the high value and the low value items are determined by you. So the cutoff is not like in MUS, does not need to be exactly equal to book value divided by sample size, or some auditors in the past thought that this cutoff should be, I don't know why, 2% of the expenditure. Not at all. The cutoff is completely based on your professional judgment. And the other thing is that you should look into the file of your population. Usually it's easy because if you have a population of just 40 operations, this is not problematic. And by doing this, you can decide what is the, let's say, the point that makes sense to separate the high value items from the low value items. Now, what else should I add to this stratification. It should be, this cutoff point can be adapted to the population characteristics, as I said, and it is possible to use more than 2 expenditure-based stratums, 3 or more, but usually we don't use many stratum because statistical samples have small sample size, and then you don't have enough samples to cover all the stratum. By the way, under non-statistical sampling, you can also do a full audit of the high-value items. Imagine, remember, if you have a high-value item, you can consider to do a full audit. But sometimes under non-statistical sampling, sometimes this is not just possible. Why? Because sometimes you don't have enough sample size to cover the high-value items. Example, imagine that you have a population of 50 items, okay? You have 10 high-value items and 40 low-value items. If you have a sample size of 5, there is no way you can fully cover the high-value stratum. You have 10, you just have 5 available in your sample. So this is not a problem. In non-statistical sampling, it's perfectly possible that the high-value group is also observed through sampling. So if you have a sample size of 5, maybe I would like to increase to 6. I will put 3 here and 3 here, 3 items in each stratum. The high-value items are not exhaustively observed, but it is not necessary. The only thing that we recommend you to do is that the sampling fraction in the high-value group should be larger than the sampling rate in the low-value group. Example, in my example, if I put 3 items in each group, I am observing 30% of the high-value items, but a much less percentage of the low-value items, which is okay and recommended, okay? Try to increase the coverage of the high-value items, but do not think that it is mandatory to observe them all. If it is not possible to identify, or if you consider that there is no any relevant stratification criteria that could be used to improve the quality of the sample, you can simply select your sample, non-statistical sampling, directly from the population without any stratification at all. This is not problematic. Sample size, it's empirically determined. For the 1420, the coverage of the sample should be at least 5% of operations and 10% of expenditure. As many of all of you will already know, this will be changed for the post-2020, but let's see that tomorrow. But for now, the minimum threshold is 5 and 10. Please remember that these thresholds are for what we consider the best case scenario. And the best case scenario means category 1 systems. So for systems with a categorization higher than category 1, you should consider to increase these coverages. How? Well, we have here in a suggestion that is in the guidance note on sampling, which is by taking into consideration the characterization of the system, to implement a gradual increase in this coverage. So for category 2 systems, to consider to audit 5 to 10% of the operations and 10% of the expenditure. For category 3, 10 to 15% of operations and 10 to 20% of expenditure. And for category 4, 15 to 20% of operations and again 10 to 20% of the expenditure. Okay, these are suggestions on how to increase the sample size or the coverage for other categories of the systems, but this is basically based on professional judgment. How do you select a sample under non-statistical approach? Either, sorry guys, I see some questions going on. You have to give an opinion per program? No, not at all. You don't need opinions per program. Secondly, is it possible to use two-period sampling in non-statistical sampling method? Yes, of course, completely. We don't have in this introductory training time to deal with multi-period approaches, but of course, multi-period approaches are very much welcomed for non-statistical sampling also. which limit for the non-statistical sampling is applicable in case we group old and new programming. Okay, we'll talk about these things of the thresholds for tomorrow. So the selection of the sample needs to be probabilistic, as I said, and you select the sample either with equal probability, as in simple random sampling, or with probability proportional to expenditure, as done in the MUS case. Okay, exactly the same thing. How to project the errors? Well, ladies and gentlemen, the projection of the errors are exactly as we have seen for MUS and for simple random sampling. Follow me. If I select my items with equal probabilities, I will project the errors as we have learned for simple random sampling. How? Using either mean per unit or ratio estimation. If I'm selecting the items with probability proportional to expenditure, like in MUS, so we are just doing a simplified version of MUS, what do? We project the errors using the MUS formula, which is, you remember, sum of the error weights multiplied by the sampling interval. And if you are using a stratified version of MUS, you use the same estimation as we have seen a few minutes ago for stratified MUS. So the formulas for projecting the errors in the context of non-statistical sampling don't have any difference in what we have seen for the statistical methods counterpart. Equal probability selection uses the formulas of simple random sampling. Probability proportional to expenditure selection uses the formulas of monetary unit sampling. In short, if I have an exhaustive group in the population, the error of the exhaustive group, as before, it's just the sum of the errors that you have found there. There is no projection to perform. For the sampling groups of the population, if you are using equal probabilities, you use the formulas that we have seen early today for, or in the afternoon, for simple random sampling. So mean per unit estimation or ratio estimation. If you are using MUS, you use the formulas that you have seen before today, which is sum of error weights multiplied by the sampling interval, which is what we have learned before. If you have a mixture between the exhaustive groups and non-exhaustive groups, also as before, the total projected error is nothing more than the sum between the error found in the exhaustive group and the error projected in the non-exhaustive group. And that's it. You have the total projected error. And then you ask me, but what about next step? There is no next step, ladies and gentlemen. There is no precision, there is no upper error limit. So how do we take our final decision? Well, unfortunately, the only way that we can use, besides other, of course, qualitative issues, but the only way that you have available from this sample to decide about the possible existence of material error is to compare the projected error with materiality threshold. If the projected error is below the tolerable error, or in other words, if it is below the materiality threshold, we consider the population does not contain material error. If the projected error is above the materiality threshold, we consider that the population contains material error. It's a very, I understand, simplistic approach, because there is no control of the audit risk. By the end of the day, we don't know how likely it is that we are right or we are wrong, but we are doing our best job possible in order to try to issue an audit opinion, okay? Just based on comparison the projected error and materiality threshold, and this means, of course, needless to say, you know this, that we have, by doing this, eliminated the third possibility of inconclusive results. In this case, results are always conclusive. Either we have material error or we don't have material error. We don't have the situation of the inconclusive results because we don't have an upper error limit to compare with materiality threshold. Another question, in non-statistical sampling and a population of 50, if a high value item, let's say 25%, generally higher than 10 of the total expenditure, how many low value items you would select, considering that you have already reached very, very good point. let's say, under non-statistical sampling, we still have a recommendation that is a kind of soft recommendation because it's not a strict statistical rule like under statistical sampling, but we recommend as much as possible that for the low value stratum, you also have at least 3 items, okay? So I would say that we would like to have a minimum sample size of 3 items, but of course there are audit authorities that have used 2 items in some stratum. I would say never less than 2 items in a stratum. Please don't forget that Konstantinos Takos, don't forget that even if with just 1 item from the high value or exhaustive stratum, even if just 1 item, you already cover 10% of the expenditure. It is also true that you need to cover at least 5% of the items, and this may mean that if you have a population of 50, 5% is 3 items. So at least 3 items would have to be audited under this rule. So imagine that you have a very high item for a population of 50, probably you could do the sample like this. This item plus a sample of other 2 items randomly selected, although in my case, I would prefer to see 3 items randomly selected. But if you decide to use 2, the Commission, I believe, won't pose any problem regarding that. Yes, Konstantinos, if 3 items exceed 50%, you still need to select low value items. This is very, very good point. Never, imagine that you need 3 items in your sample at least. Never exhaust your 3 items just with high value items, because please remember that our rule is that all the items in the population need to have a probability to be selected to the sample. So ideally, just use 1 high value item and save the other 2 to guarantee that all units in the population have some selection probability. Welcome. Francesco Pirone, each stratum should be represented in this case. I don't know if I understand the question, but if you have this high value stratum composed by just 1 item, I don't know if this is the case, and then you have 49 additional items, then you need to select a sample of ideally 3 items from this 49 in order to guarantee that all the items and both stratum, let's call this both stratum, are represented in the sample. Good. Ladies and gentlemen, you already know we don't calculate upper area limit, so we don't have control of the audit risk. Let's see a numerical example to put things in perspective. I have a population of 48 operations, so it's clearly for non-statistical sampling, expenditure of 10.4 million euros. So we are going to use non-statistical sampling. By the way, for the sake of the example, with certification of the high value operations. So this is a summary of the population. The audit authority decided to use, looking at the file of the population, a cutoff value of 5% of the book value to implement this certification. And this is a summary of the population. So we have set a cutoff like this, above which we have 12 high value items, and below which I have 36 high value items. You already suspect there is no way that I can observe exhaustively the 12 items. There is not enough sample size to do so, but it's not problematic at all. I will select a sample here, another sample here. Let's see. And also the division of the sample between the 2 stratum is completely empirical based on your professional judgment. Let's see the example. Imagine that in this case, I have a category 3 system. For a category 3 system, let's see what is the recommendation. For a category 3 system, let me aim, so it's here, let me aim to audit 15% of the items and 20% of the expenditure. Okay, let me aim this 15 and 20. So to audit 15% of the items, it's very simple. I will multiply 48 by 15% and it gives me 7.2. As you know, sample sizes, when they have decimal parts, they always have to be rounded up, which means that I have to round to 8. So I've decided that I'm going to audit 8 operations out of this population of 48 operations. Now, as usual, I cannot audit the full high value stratum, but I will try to have a higher coverage of this stratum. How? It's absolutely subjective based on professional judgment, but this audit authority decided to do this. 50% of these 12 high value items, so a sample of 6 here, and 8 minus 6 is 2 here. They decided to do this. Because we have this recommendation, again, it's not mandatory, it's just a recommendation, that we would like to have 3 items per stratum. Let's suppose that the audit authority decide to increase this from 2 to 3. So by the end of the day, they will have 6 operations from the high value stratum plus 3 operations from the low value stratum. So in practical terms, they have increased the sample size from 8 to 9. Okay, this is the final sample size. Now, second thing, I'm covering 15% of the operations, but I also have to coverage 20% of the expenditure. Is it expected that I will coverage 20% of the expenditure? Of course, yes. Why? Because we have audited a larger percentage of the high value items. And in fact, this is a good trick for you to guarantee that you achieve the coverages in terms of expenditure. In fact, there are 2 things that you have in your power to increase the coverage in terms of expenditure. One is to audit a larger percentage of the high value items, and by this, you increase the audited expenditure. Another technique is to select the items, instead of selecting the items with equal probabilities, to select the items with probability proportional to expenditure, like in MUS, and by doing so, of course, you also increase the coverage of your sample in terms of expenditure. Okay, and this was done in this case. So by the end of the day, then what do we do? Okay, I have a sample of 6 high value operations in the high value stratum. By the way, no errors were found. And I have a sample of 3 operations in the low value stratum, let me call it like that. And we identified an errors of 4.4 thousand euros with an audited expenditure of 673,000. So what do we do now? Sorry, this is not the errors. This is the audited expenditure. Sorry, guys, just to explain that, in fact, you have coverage more than 20% of the expenditure. Next step would be to decide if we use mean per unit or ratio estimation, okay? Let's not go into that detail. Let's assume that I have checked this formula and this supports ratio estimation. How do I project the errors, okay? So, sorry, this is the error and this is the amount. So, high value stratum, how much are the errors? 0. No errors were found in the high value stratum. How do I project errors in the low value stratum? Book value of the low value stratum, 2.8 million euros, times what? The error rate of the low value stratum. How much is the error rate? The error found in the sample, 4.4 thousand euros, divided by the audited expenditure. 4.4 divided by 600 something gave me a total projected error of 18,000 euros. And it's done. No precision, no upper error limit. Why? Because now the only thing that I can do is to compare this projected error with materiality threshold. For a population of 10 million, the tolerable error, 2%, is 208,000 euros. Because the projected error is 18,000, so much smaller than the materiality threshold, which means that in this case, we would conclude that the population does not contain material error, although, of course, we have not done any control of the audit risk, we have not calculated precision, and we have not calculated the upper error limit. Okay? And that's it, all about non-statistical sampling, right on time to finish our seminar for today. So still 5 minutes if you want to have some questions. Guys, profit now to open your microphones or to write your questions. Guys, good. This is a very important thing, which is in sampling, there is a very basic and probably one of the most important rules. All the units in the population need to have some chance to be selected to the sample. Second rule, this chance does not need to be equal for all the population items. In fact, when we are using MUS, we are already distorting the selection probabilities. And when we stratify by different stratum, as in this example, look guys, and I have placed 6 items in the high value stratum and 3 items in the low value stratum, I am already distorting this probability. You all understand that the high value items in my example have much larger selection probability than the low value items. Of course, I'm selecting 6 out of 12 here and 3 out of 36 here. The high value ones have much larger selection probability, no problem. And even within one stratum, even within this low value stratum of the 36, if you'd like to select the 3 items with probability proportional to expenditure, yes, you can also select with probability proportional to expenditure. It's not necessary that within one stratum, all the items are selected with equal probabilities. Okay? Any final questions? If not, ladies and gentlemen, for the ones that will follow us tomorrow, see you tomorrow at the same time by 9:30 Brussels time.